Ever find yourself thinking back to school and wondering, when will I ever use this stuff? Like trigonometry, I
Yeah.
mean, sines, cosines, tangents, that whole thing.
Yeah, yeah.
Turns out it's way more practical than you might think.
Oh, absolutely.
It's how we figure out, like, how tall buildings are or how far apart things are without actually having to measure them directly. It's wild.
It's pretty amazing when you think about it. And that's actually what we're going to be digging into today, how those trig ratios, the sine, cosine, and tangent, can be used to figure out the heights and distances of objects. We've got some interesting real-world examples in our source material here.
Oh, cool.
Stuff like how to figure out the height of a tower, what length the ladder needs to be, even how to measure across a river,
Yes.
all sorts of practical applications.
Before we get into the cool stuff, let's make sure we're all on the same page.
All right.
So imagine you're looking at something, let's say, like a tall tower.
Okay?
The line between your eye and the top of the tower, that's your line of sight. And then the angle between that line of sight and the ground, if you're looking up, that's the angle of elevation.
Yeah.
Our source has a nice little picture of this, by the way. Figure 9.2 if you want to check it out.
Mhm.
Now, imagine you're on top of the tower looking down at something on the ground.
Okay.
That's your line of sight pointing down.
Right.
And the angle between that line and the horizon, that's your angle of depression.
Makes sense.
Our source has got a figure for this one too, figure 9.3.
Mm-hmm.
So it's all about the line of sight, and whether you're looking up or down, that's what forms these angles.
Exactly.
Now, here's the question.
Okay.
How does knowing that angle and maybe one distance let you figure out, like, the height of the tower or something? What's the secret sauce here?
Well, the key is in understanding right-angled triangles. If you've got a tower standing straight up the ground and your line of sight to the top of the tower, boom, you've got yourself a right-angled triangle.
Oh, I see.
And those trigonometric ratios, they're like the code that links the angles inside that triangle to the lengths of the sides. So if you know one angle, like the angle of elevation, and the length of one side, like how far you are from the tower, you can use these ratios to figure out the other lengths, even if you can't directly measure them. Pretty neat, huh?
So let's try it out with a real example.
Right.
Our source starts with this one about finding the height of a tower. Okay, so picture this. You've got a tower, stands straight up. You're standing on the ground 15 meters away from the base of that tower.
Okay.
You look up to the top, and your little angle measurer thingy tells you the angle of elevation is 60 degrees. They've got a diagram for this in the source, figure 9.4. How would you figure out how tall the tower is?
All right, this is where the tangent comes in handy. The tangent of an angle in a right triangle, it's basically a ratio. It tells you the length of the side opposite the angle compared to the side next to the angle.
Okay.
So in our tower scenario, the opposite side to that 60-degree angle is the height of the tower. We can call it AV for simplicity. Got it.
The adjacent side is the distance you are from the tower, which we know is 15 meters. So the tangent of 60 degrees is equal to AB divided by 15 meters, or in short, tan, 60 degrees equals AB 15.
And I remember from back in the day, the tangent of 60 degrees is like the square root of 3.
That's right.
So we've got an equation now. Square root of 3 equals AB over 15. To find AB, the height of the tower, we just need to multiply both sides of the equation by 15.
Yep, and that gives you the height of the tower. AB would be 15 times the square root of 3 meters, which, if you want to get an idea, it's about 25.98 meters.
Wow, that's pretty high.
Yeah.
So like if you're in a city, you look up at a skyscraper and wonder how tall it is.
Yeah.
You can actually use this to get a rough estimate.
Absolutely. It's really practical.
No need to climb the building with a measuring tape.
Exactly.
Okay, the next example in the source takes things a step further.
Okay.
This one involves an electrician.
Okay.
They're trying to fix something on a pole, a 5-meter tall pole, and they need to reach a spot that's 1.3 meters below the top.
Got it. They're going to use a ladder that's inclined at 60 degrees to the ground.
Okay.
So the questions are, how long does that ladder need to be?
Okay.
And how far from the base of the pole should they place the bottom of the ladder to make sure they get to the right spot safely?
Right.
They've got a figure for this one too, figure 9.5.
Mm-hmm.
First, let's figure out what height the electrician needs to reach on the pole, right?
Yep.
So the pole is 5 meters tall. They need to be 1.3 meters from the top. So that's 5 minus 1.3.
Right.
That means they need to be 3.7 meters up the pole. That's the height the ladder needs to cover.
Exactly. Now think about the ladder leaning against the pole. It's like the longest side of a right-angled triangle, the hypotenuse.
Right.
The ground is one of the shorter sides, and the pole, up to that 3.7-meter mark, is the other shorter side. We know the angle between the ladder and ground is 60 degrees, and we know that opposite side is 3.7 meters. So we're looking for the hypotenuse, which is the ladder's length. For that, we use the sine. Sine of an angle is the ratio of the opposite side to the hypotenuse. So sine of 60 degrees equals 3.7 meters divided by the length of the ladder, which we can call BC.
Sine of 60 degrees, that's square root of 3 divided by 2, right?
Right.
So I've got the equation square root of 3 over 2 equals 3.7 over BC.
Exactly.
We want to find BC, so rearrange it a bit, and it becomes BC equals 3.7 times 2, all divided by square root of 3. And according to our source, that works out to be about 4.28 meters.
That's right. So that's how long the ladder needs to be.
Okay, and what about the second part of the problem? How far from the pole does the ladder need to be?
Right. That's the adjacent side of our triangle, right next to that 60-degree angle. We've got the opposite side, 3.7 meters, and the angle. Perfect setup for the cotangent. Cotangent is just adjacent side divided by opposite. And for 60 degrees, it's 1 divided by the square root of 3.
Okay.
So cotangent 60 degrees equals, let's say, DC, that's our unknown distance on the ground, divided by BD, which is our 3.7 meters.
All right, so we've got 1 over square root of 3 equals DC over 3.7. Multiply both sides by 3.7, and we get DC equals 3.7 divided by square root of 3.
Exactly.
And our source tells us that's roughly 2.14 meters. So the electrician needs to put the ladder about 2.14 meters away from the pole.
Precisely. It's really interesting, isn't it, how trigonometry goes beyond just numbers and formulas and actually has practical uses in real-life situations.
Totally.
It's about safety, too, in this case.
Yeah, very important.
Making sure the electrician's up there safe and sound.
All right, let's move on to another example. This one's about an observer, and they're looking at a chimney.
Okay.
The observer is 1.5 meters tall, standing 28.5 meters away from the chimney, and the angle of elevation from their eyes to the top of the chimney is 45 degrees.
Okay.
We need to find out how tall that chimney is.
Got it.
We've got a diagram for this one, figure 9.6 in our source.
Hmm.
Now, here's a thing to remember. That angle of elevation is always measured from the observer's horizontal line of sight, right?
Right.
Which in this case is from their eyes, not from the ground level.
Exactly. We got to factor in the observer's height.
Right. So imagine a line from the observer's eyes going straight towards the chimney. That line and the ground make a right triangle.
Okay, yeah.
The distance on the ground, the 28.5 meters, that's the base of the triangle.
Right.
And that 45-degree angle, that's one of the angles.
Yes.
The height of that triangle is going to be the height of the chimney, but only the part above the observer's eyes.
Exactly.
Yeah.
So we got to add the observer's height later to get the full height of the chimney.
Okay, good point. Let's call the height of the chimney above the observer's eyes, let's call it AE.
Okay.
We know DE, the distance on the ground, is 28.5 meters.
Right.
So triangle ADE, 45 degrees at D, tangent time again.
Yep.
Tan 45 degrees equals AE over DE.
And the tangent of 45 degrees is just 1.
Exactly.
Nice and simple.
So 1 equals AE over 28.5 meters. That means AE, the height above the observer's eyes, is also 28.5 meters.
Right. But don't forget, we want the total height of the chimney.
Right. We got to add the observer's height, which is 1.5 meters.
Exactly.
So 28.5 plus 1.5, that gives us 30 meters.
That's it. The chimney is a nice round 30 meters tall.
So always got to remember to consider the reference point for those measurements.
Absolutely. It can make a big difference.
Okay, ready for the next one? Example 4.
Lay it on me.
This one gets a bit more complex.
Okay.
We've got a building 10 meters tall, and on top of it is a flagstaff. From a point P on the ground, someone measures the angle of elevation to the top of the building, and it's 30 degrees.
Okay.
Then, from the same point P, they measure the angle to the top of the flagstaff, and that's 45 degrees.
Got it.
We need to figure out how long that flagstaff is and how far point P is from the building.
I like a challenge.
Figure 9.7 in the source is the visual for this one. Now, this is interesting because we actually have 2 right-angled triangles.
Oh, I see.
They share one side, the distance from point P to the base of the building.
Right.
Let's call that PA.
Okay, Pete.
First, let's focus on the smaller triangle, point P, the base of the building A, and the top of the building B.
Go.
We know AB, the building height, is 10 meters, and the angle is 30 degrees. Tangent time. Tan 30 degrees equals AB over PA.
You got it. And tan 30 degrees is 1 over the square root of 3.
Right. So 1 over square root of 3 equals 10 over PA.
Yeah.
Solving for PA, we get PA equals 10 times the square root of 3 meters, which is, according to the source, about 17.32 meters.
So that's the distance from the point to the building.
Yep. Now let's look at the bigger triangle, point P, base of the building A, and the top of the flagstaff, let's call that point D.
Okay.
Angle of elevation to the top of the flagstaff is 45 degrees. The total height, AD, that's the building height plus the flagstaff, right?
Right.
So AD equals 10 plus, let's say, X for the length of the flagstaff.
Okay, makes sense.
Tangent again. Tan 45 degrees equals AD over PA.
And tan 45 degrees is just 1.
Right. So 1 equals 10 plus X all over PA. And we know PA is 10 times the square root of 3.
Right.
Substitute that in.
So we get it 1 equals 10 plus x over 10 square root of 3.
Exactly. Multiply both sides by 10 square root of 3. We get 10 square root of 3 equals 10 plus x. And to get x, the length of the flagstaff, we just got to subtract 10 from both sides. So x equals 10 square root of 3 minus 10.
Okay.
Or another way to write it, 10 times square root of 3 minus 1.
Right, right.
And our source says that's about 7.32 meters.
So the flagstaff is about 7.32 meters tall.
Yep.
That's pretty cool how we can break down these problems into multiple triangles and solve them step by step.
Yeah, trigonometry can be pretty powerful when you know how to use it. All right, the next example in our source looks at how the shadow length changes depending on the sun's angle. It says the shadow of a tower is 40 meters longer when the sun's altitude, meaning the angle of elevation of the sun, is 30 degrees compared to when it's 60 degrees.
Okay, so the height of the tower is staying the same.
Right.
It's the angle of the sunlight that's causing the difference in the shadow.
Exactly. So let's say the height of the tower is h, and the length of the shorter shadow when the sun's higher at 60 degrees is x.
Okay.
When the sun's lower at 30 degrees, the shadow is x plus 40 meters long.
Right. That makes sense.
We can use the tangent for both situations.
Yeah.
When the sun's at 60 degrees, tan 60 degrees equals the height of the tower, h, divided by the shorter shadow, x. That simplifies to square root of 3 equals h over x, or h equals square root of 3 times x.
Okay, good. Now for the 30-degree angle.
Right. Tan 30 degrees equals h over x plus 40.
Right.
Simplifies to 1 over square root of 3 equals h over x plus 40.
Okay, so now we have two equations, and we have two unknowns, h and x.
Exactly.
We can definitely work with this.
And since our first equation already tells us what h is in terms of x, we can substitute that into the second equation.
Smart move. Let's do it.
So 1 over square root of 3 equals, instead of h, we put square root of 3 times x, and that's all divided by x plus 40.
Okay.
Cross multiply, and we get x plus 40 equals square root of 3 times square root of 3 times x, which simplifies to x plus 40 equals 3x. Subtract x from both sides.
And we get 40 equals 2x.
Exactly. So x is 20 meters. Now we know the shorter shadow.
Right.
We can go back to our first equation, h equals square root of 3 times x, plug in x equals 20, and we find the height of the tower is 20 times square root of 3 meters.
Wow, that's a pretty clever way to find the height, just by observing the changes in the shadow lengths and the angles of the sun.
Yeah, it really shows how those angles and distances are connected. All right, ready for example 6.
Hit me with it.
This one's about two buildings.
Okay.
From the top of a taller building, the angle of depression to the top of a shorter building is 30 degrees.
Okay.
And the angle of depression to the bottom of the shorter building from the same spot on the taller one is 45 degrees.
Got it.
The shorter building is 8 meters tall. We got to find the height of the taller building and the distance between them.
Okay, so we're dealing with angles of depression this time.
Right. But the important thing is that they're related to angles of elevation.
Oh, how so?
Imagine a line going straight out from the top of the taller building. The angle of depression to the top of the shorter building is 30 degrees below that line.
Okay.
Which means if you were standing on top of the shorter building looking up, the angle of elevation would also be 30 degrees.
Oh, I see. They're like alternate interior angles or something.
Exactly.
Yeah.
And the same goes for the 45-degree angle of depression to the bottom of the shorter building. From the bottom looking up, it'd be a 45-degree angle of elevation.
Right, right. That makes sense.
Okay, so we've got our taller building. Let's call it PC for the height. And the shorter one, AB, 8 meters tall. The distance between them, let's call it AC, which is also BD in the diagram. Now, let's say the taller building is h meters tall. That means the part of the taller building that's above the height of the shorter one, that's PD, would be h minus 8, right? Because
Okay.
AB and DC are both 8 meters.
Okay, got it.
Now we've got two right triangles we can work with, PBD and PAC.
Right.
Triangle PBD angle at B is 30 degrees. Tangent time. Tan 30 degrees equals PD over BD.
So that's 1 over square root of 3 equals h minus 8 over bd.
Right. And in triangle PAC, angle at A is 45 degrees. tan 45 degrees equals PC over AC.
So that's 1 equals h over ac.
Exactly.
And since AC and BD are the same distance, we can also say 1 equals h over BD, which means BD just equals h.
Right. Now we've got some equations to play with. From the first one, we can say BD equals square root of 3 times h minus 8. And from the second, BD just equals h.
Clear.
So they both equal BD, so we can set them equal to each other. H equals square root of 3 times h minus 8.
Makes sense.
Expand that right side. H equals square root of 3 times h minus 8 times square root of 3. Rearrange to solve for h, and we get 8 times square root of 3 equals square root of 3 times h minus h.
Okay.
Or 8 times square root of 3 equals h times square root of 3 minus 1.
Right.
Now, to isolate h, we just got to divide both sides by square root of 3 minus 1. So h equals 8 times square root of 3, all divided by square root of 3 minus 1.
Okay, and to get rid of that square root in the denominator.
We can multiply both the top and bottom by square root of 3 plus 1. That gives us h equals 8 times square root of 3 times square root of 3 times square root of 3 plus 1, all divided by 3 minus 1, which simplifies to 24 plus 8 times square root of 3 over 2.
I'm following.
And that becomes 12 plus 4 times square root of 3. Our source writes it a bit differently, 4 times 3 plus square root of 3 meters.
Okay.
And since the distance between the buildings, AC, is the same as BD, which is h, that distance is also 4 times 3 plus square root of 3 meters.
Pretty neat how we can figure out all that just from those angles.
Yeah, trigonometry is pretty handy for dealing with multiple objects and angles. All right, ready for the last one? Example 7.
I'm ready. What have we got?
This one's about a bridge over a river.
Okay.
From a point in the middle of the bridge, 3 meters above the water, the angle of depression to one bank is 30 degrees, and the angle of depression to the opposite bank is 45 degrees.
Got it.
We need to find the width of the river.
Okay. Sounds interesting.
They've got a nice diagram for this one, too, figure 9.0.
Okay.
So the bridge is 3 meters high. Let's call the point on the bridge P, and the points directly below it on the banks, let's call them D.
Okay.
So PD, that vertical distance, is 3 meters. Let's say the river banks are A and B.
Right.
Angle of depression from P to bank A is 30 degrees, and to bank B is 45 degrees.
Okay, I'm picturing it.
And just like before, those angles of depression are the same as the angles of elevation if you were standing on the banks looking up.
Right, because of those alternate interior angles.
Exactly.
We've got our triangles again.
Yep. 2 right triangles, APD and BPD, both share the vertical height, PD, which is 3 meters.
Okay.
So in triangle APD, the angle at A, that's the angle of elevation from bank A to the bridge, is 30 degrees.
Right.
Tangent time. Tan 30 degrees equals PD over AD.
So that's 1 over square root of 3 equals 3 over 80.
Right. Solve for AD, which is the distance from that point below the bridge to bank A, and we get AD equals 3 times square root of 3 meters.
Okay, and now for the other triangle.
Right. Triangle BPD, angle at B, the angle of elevation from bank B is 45 degrees, tangent again. Tan 45 degrees equals PD over BD.
So that's 1 equals 3 over BD.
Exactly. And solving for BD, the distance to bank B, we get BD equals 3 meters.
Nice.
Now those two distances, AD and BD, they make up the total width of the river.
Right.
So add them up. 3 times square root of 3 plus 3, which is 3 times 1 plus square root of 3 meters.
That's the width of the river.
Yep. Pretty cool how trigonometry can help us measure across things we can't easily get to, like a river.
Absolutely. And it makes you realize that a lot of these calculations might be happening behind the scenes in things we use every day, like GPS.
Yeah, totally. GPS, drone surveying, all sorts of stuff. It's all based on these same principles. It's pretty amazing.
It is. And I think the biggest takeaway here is that those trig ratios, they're not just abstract formulas. They're powerful tools for measuring things indirectly.
Exactly. And when you think about all the different areas where this stuff comes into play, surveying, navigation, construction, even things like figuring out the best angle for a slide in a park, it's really mind-blowing.
It is.
Like, how do GPS systems work so accurately? How do drones create such detailed maps?
It's all about those angles and distances, just on a much larger scale and way more sophisticated.
Yeah.
But the basic ideas are the same. It's pretty incredible how these mathematical concepts help us understand and measure the world around us.
Definitely something to think about.
It is.
Thanks for joining us for this deep dive.
My pleasure.
It's been a real eye-opener.
It has.
Until next time, keep those angles in mind.
You bet.